Hello, everyone. So today we're going to be looking a lot at how the stability of a compound changes with pressure. So time to look a little bit more at Gibbs. So last time we were focusing on the temperature dependence of Gibbs. Today we're going to focus in on the isothermal pressure dependence of Gibbs. So again, we're going to be making the assumption of isothermal conditions. If you do have a temperature change, well, we've got a state function and you can treat pressure and temperature as independent functions because yay for state functions. So when dealing with the pressure dependence of Gibbs, we're going to be focusing very specifically in on the molar version of changes of Gibbs, which means we're going to be talking a lot about the molar entropy of our solid. Because again, we don't want to deal with uh, arbitrary amounts of a species and want to put everything on as much of an even playing field by working with molar properties as possible. So if I'm going to be looking at the change of Gibbs with pressure, well, we can go ahead and express this in the integrated form as my final Gibbs energy will be equivalent to my initial Gibbs energy plus this kind of odd integral of our molar volume with respect to pressure. Well, here's going to be the issue. As we've seen before, volume is very frequently a pressure-dependent property. And so how the volume is going to change with pressure is going to be very dependent upon the scenario that we're dealing with. So we're going to start with almost the easiest case of a condensed phase, say a solid or a liquid. So our question is going to be, how does our volume change with pressure for one of these condensed phases? Well, in general, unless I'm putting a real ton of pressure on top of, say, water, it's more or less going to have the same density or molar volume. So in general, it's going to stay relatively fixed, which makes this integral positively easy because molar volume then becomes a constant. It pops out front, and then any change of Gibbs is going to be related to the to the simple difference in my final and initial pressure, which ends up giving us quite a nice equation. However, it is worth noting that as I apply additional pressure, my actual volume will very slightly decrease. However, this difference is often minor enough that unless I'm dealing with several thousand bar of pressure, I can frequently get around ignoring this. However, if you want to improve the accuracy of your results, go ahead and try and determine a pressure dependent volume for your condensed phase. Again, this is mostly going to be important for liquids, but for most solids, we can treat this value as fixed. So let's go ahead and examine what sort of influence this will have on our changes of free energy by looking at a couple of systems. So let's go ahead and work with one liquid, water, with a molar volume of about 18 milliliters per mole, as well as two solids, graphite and diamond. Well, graphite has a molar volume of about 7.9 milliliters per mole, and diamond with about 5.1 milliliters per mole. So if I want to figure out the free energy for the compression of water, well, then I go ahead and just insert my molar volume. And if I go from 1 bar to 2 bar, so I doubled the pressure, which actually does take a fair bit of energy, well, I'll simply have my molar volume times 1 bar, because that's the difference of final minus initial. And then it's important to make sure that we convert from liter bar to to joules. So it turns out there's about 100 joules in 1 liter bar. And that's actually a fairly useful metric to know when we're, say, dealing with work or some of these conversions from PV units to simple energy. So in other words, it's going to require about 1.8 joules of energy for every mole of water I'm compressing. And this is even assuming no change in volume. So it actually does take a fair bit of energy just in essentially compacting our bonds, even if no structural changes occurred. And this is actually fairly useful to think about. However, the more compact that material is, essentially the more built it is to resist this. So for graphite, we see almost half the change of if we only end up seeing the graphite destabilize by about zero 0.8 joules per mole. And for diamond, it's almost a third of that of water. It's less than a third of that of water, of about 0.5 joules per mole. So not a lot of energies is going to go in this. Because again, this is individual joules, which is kind of chump change for chemical processes. Now, if I was going to say increase the pressure to 1,001 bar, so I essentially put in an extra 1,000 bar of pressure. So this is a whole lot of pressure. It have to get to pretty special circumstances to reach a megabar, or sorry, a kilobar. Well, for water, this only ends up being about 1.8 kilojoules per mole of energy. So water actually is almost as stable as it always has been. Graphite, again, sees a very minor increase, and diamond the same. Because we see this kind of linear increase of energy with pressure, and our values were already so low to begin with, a lot of times it's very natural to essentially ignore the influence of increasing the pressure on the free energy of a complex, simply because these energies are so low to begin with. However, what can actually become a little bit more important is when we're dealing with the influence of pressure when looking at a Gibbs energy of transition. So if I'm going in between two condensed phases. So let's say I'm interested in trying to change graphite into diamond, because let's be honest, there's a lot of people who want to try and turn your pencil lead into something a little more valuable. So let's go ahead and figure out whether increasing pressure is going to favor or disfavor this process. So in order to do this, I need to figure out how both of these two properties are going to increase or decrease with pressure. So this is very similar to what we've done with our other thermodynamic cycles. So our Gibbs free energy at our new pressure is going to be our old value plus, again, the molar volume of diamond times the change in pressure, and similar for graphite. So I can then insert both of these equations, and my Gibbs free energy of transition at my new pressure is essentially going to be my old pressure for diamond plus the correction minus the old energy for graphite, again, plus the new correction. So we can then try and isolate our Gibbs free energy components and our molar volume components. So we're going to have our old Gibbs free energy of transition is equal to our old Gibbs energy of transition plus what essentially is our change in molar volume with our transition. So going from our old complex, graphite, to diamond, times, again, this change in pressure. So if I'm looking at trying to turn graphite into diamond, well, it turns out that this has a molar volume of transition that is a negative value of about -2 milliliters per mole. But this actually has a really important influence, because we can also put this in terms of energy units. And what we find is it's going to have a negative value of about 0.3 joules per bar, which means that for every bar of additional pressure I put on the system, I'm going to stabilize my product, diamond, by about 3 joules, which means if I put the system under a kilobar or 1,000 joules of additional pressure, well, it turns out I now favor the formation of diamond by 3 kilojoules. And if you're able to hit, say, a megabar, so if I'm able to put the system under a full extra million bars of pressure, which you can hit under really severe circumstances, well, then at that point, I favor the system by megajoules of energy per mole. So if you hit those extreme circumstances, you are going to form diamond just sheerly based on the pressure. However, as you may have noticed, in order to really make big influences to the stability of either individual species or reactions, we often have to hit very high pressures. So typically, this is more the domain of a lot of geoscientists who often deal with these extreme pressures. However, certain mechanical and chemical engineers do often deal with, say, kilobars of pressure in real industrial settings, as compressed gases are a very good way to drive reactions. So you do have to occasionally worry about how our free energy is going to change with these pressures. However, much more common, we're going to be interested in how the stability of a system changes with pressure if it's a gas. So, when working with gases, our usual instinct is to be lazy and assume the ideal gas. And if I'm assuming the ideal gas, well, it turns out that this molar volume dependence that I have to integrate, well, that's just going to be equal to RT over P. Well, at this point, I can then pull my constants RT out in front of the integral, and I'm left with the integral of dP over P. Well, at this point, this integral should look real familiar with you, for you. So our difference in free energy upon the application of pressure is literally going to be RT times the natural log of our final pressure over the initial pressure. But oftentimes, our initial pressure that we're concerned with is going to be a reference pressure, often standard state or 1 bar. And this is often a very important value to be concerned with as an initial pressure, is if I'm going to, say, go determine my free energy of a compound, say the free energy of formation of methane, because I'm interested in running a chemical reaction, well, the only energy I'm going to find is for 1 bar methane. So guess what? We're going to have to make any corrections to that free energy manually. And as long as we assume that it's behaving as an ideal gas, it's a relatively simple correction of RT ln of our new pressure, because ln of 1 goes to 0. But it's worth noting that this is here just to help correct for our units. And so in general, we're going to be applying this equation to a lot of ideal gas systems. And let's go ahead and get an idea of what these numbers look like for relatively similar pressure influences that we did for our condensed phases. So let's do this good old increase of pressure of, say, steam, so now gaseous water, from 1 bar to 2 bar. Well, under this case, it ends up being RT ln of 2, because again, RT doesn't change, ln of 2 over 1, so this ends up having a value of 1.7 kilojoules per mole. Now, I want to emphasize that this is the same amount of free energy increase that I saw in liquid water if I went from 1 bar to 1,000 bar. So it's worth noting that gases are going to be much more vulnerable to pressure changes. So we're going to often have to take into deep consideration how pressure changes for these gaseous systems. And this actually becomes even more important because it turns out that if you go down in pressure, well, this is going to become quite important because all I care about is the ratio. So the difference in between 1 bar and 2 bar is more or less the same energy difference as 0.5 bars and 1 bar, or 0.1 bars and 0.2 bars. So again, all that matters is the ratio. However, let's talk about, say, if I was going to do something very similar to what I did with my condensed phases, and I go from 1 bar to 1,000 bar. Now, in this case, my ratio becomes 1,000 to 1. And it turns out that I have to put in 17.1 kilojoules per mole of energy. So this is 10 times as much. So again, it is worth noting that we do see a much more kind of dampened effect than we saw with our condensed phases. Because if I went from 1 bar to 1,000 bar in a condensed phase, it took 1,000 times as much energy, but that energy value is a lot smaller. Because of this natural log influence, if I do 1,000 times as much pressure change, or 500 times as much pressure change, then congratulations, it only takes about 10 times as much energy. So this is an important consideration. However, because it's more focused on a ratio than absolute values, this has some deep considerations as soon as you go to very low pressures, because the influence in between, say, 1 millibar and 2 millibars is just as important as 1 bar and 2 bar. And again, this is partially because we are working on a molar basis, so it does take a lot more volume to accomplish a similar amount of change. So that is worth taking into account. And it turns out that this set of equations is really going to drive a lot of our treatment of gas phase systems as we go forward through the rest of the semester. However, before we start talking about a lot of our phase changes of, say, how I'm going to mix my gases and solids, we need to account for one important thing. To generate this equation, we made use of ideal gas laws. Well, as we've talked about, especially as I'm going to higher pressures, I'm not always going to have this. So next time, we're going to have one last side jaunt into non-ideality. Till then, take care.